It's 10:20, so let's get started. We're going to be wrapping up Module 5 today on imperfections in solids. And then this will get us all set up to discuss phase diagrams and how we discuss the compositions of materials as it relates to the phase fraction itself. Because at the end of the day, you will not be working with single component materials in your engineering jobs. You'll be most likely working with composites, whether or not they contain some permutation of metals, ceramics, polymers, nanocomposites, what have you. Okay, so after today, you'll understand all about perfect crystals and then imperfect crystals. So I just sent out an announcement regarding extended office hours. This is by request. There were some additional questions from several of you regarding crystallographic directions. And since I'm addressing some of your concerns, I'm opening up the extended office hours, which is today right after class until 12 p.m., so that it's available to everyone who can make it. I understand logistically this is not possible, but in case your schedule permits and you would like to join in on the discussion, you are very welcome to do so. The individuals who have reached out to me to discuss it specifically, obviously the time works for them. And so if you're on the Monday, Wednesday schedule, if you were able to make it to my usual office hours, hopefully you can make it to this one and it is available to you as well, okay? So that way everybody has the same opportunity. Okay, with that I'll continue. Oh, one other thing, I've noticed going through some of the homework that some of you have zeros, and I know that most of you are not in the situation where you've not done your homework. I think you're in the situation where you've just not pressed the send to gradebook. So please do so, and if you have any technical problems, Brian Thurston, the TA that's dedicated to addressing all of these problems, he will be on deck to address any technical issues you may have, okay? But really, if you see a zero, please don't be alarmed. Just check if you've just hit the button. Everything should be logged. The timestamp should be there. We don't anticipate any issues. We've already dealt with some of this for homework 1, so just FYI, okay? So check your score. Please be up to date and let us know if there's any clerical errors. We're happy to address it in real time, okay? Okay. All right. Will the pen work today is probably the most unanswered question. But fear not. I brought backup for I anticipated that there might be a monitor gremlin that refuses. I guess when you passive aggressively threaten the gremlin enough, it actually does work. Okay, so we've gone over last time in great detail how to solve for vacancy concentration. Your homework also asks you to actually calculate how many total sites there are. Okay, so there will be a tutorial video going up on how to actually calculate and the total number of sites. There's also been a tutorial video posted in regards to how to manipulate the different conversions between atomic percent and weight percent. That's the majority of our discussion today, because when we talk about imperfections, we typically talk about, depending on which scenario you're in, if you're mixing the material, we typically report those numbers in weight percent because it's convenient, right? How much of phosphorus should I add into silicon to make this microchip work? It's much easier to have somebody just weigh it out, okay? Stoichiometrically, when we're discussing composition, right, we want to be talking in terms of atomic percent. Is it silicon 0.99, phosphorus 0.01, right? That's atomic percent. So depending on the scenario, we talk about atomic percent when it's convenient for us, or when we're dealing with the actual mixtures physically executing the work, it's more convenient to deal with weight percent. And so chapter 5 deals with that. And so there are two equations that just go back and forth. So this is where we left off last time. So I want to jump to that before I come back to the Humoral rules. We're going to build up to this point where we can go back and forth to talk about weight percent, denoted as C, and then atomic percent or atom percent, denoted as C prime. Now this may be very unhelpful because it gets confusing whether you're talking about C or C prime, but that is the notation. So sometimes you'll see me write it out where I write C or C prime, and sometimes I'll just write out weight percent or WT percent or AT percent. Okay, so this is what we're going to work up to today, and then we'll go through a problem about average densities, because when you mix things, inevitably, right, you're going to get some weighted average. We've talked about weighted averages in regards to polymers and how you don't always have the same number of chain length in a polymer mixture, right? So you always have a distribution. So we've already addressed weighted averages, and now we're going to extend that to talking about the molar mass, average densities, and that will wrap up our discussions on imperfections in solids. So let's get us there. Right, so the problem we left off with was talking about the vacancy concentration in a metal system at 1,000 Kelvin versus at 298 Kelvin, right? Some elevated temperature versus room temperature. And so we talked about how there could be 10 to the 10 to the 17, let's say the concentration, some ridiculously high concentration vacancy because it's thermally activated. So at higher temperatures, you're going to have immensely more vacancies than if you were at room temperature, right? It's thermally activated. So the more energy you put into the system, you're going to induce atom hopping. Atoms are now able to vibrate a whole lot more, and they can have enough energy to hop to another site. And they can keep on hopping to the point where they can hop to the edge of the material. And that could actually expand your lattice constant quite a bit. So both due to thermal expansion, but also due to vacancies that are being generated. Okay, so that's where we left off last time, is appreciating the thermal activation processes of vacancy formation and the Arrhenius, and manipulating the Arrhenius equation. So then we continue and say, okay, well, if we're not dealing with a single component, like the simple examples of just copper or just nickel having a vacancy, or self-interstitial where you move an atom to another non-crystallographic site. Okay, what happens when you have a second component? Sometimes it's an unwanted second component, whether it be a smaller atom or a same size atom. That's an impurity. Sometimes you want that because you're trying to engineer an alloy with say, higher yield strength, right? You're actually targeting some solid solution. So I think solution in everyday nomenclature, we first think of it as a solution, right? Some liquid form where you add salt in water, sugar in water. These are the typical solutions we think of, but we can also have solid solutions in which everything is in the solid form. And so when you have, let's say, mixtures of, let's say, copper atoms and nickel atoms, those will form a solid solution. You can mix in a little bit of powder of nickel, a little bit of powder of copper, or 2 ingots, increase the temperature, melt it all together. But how can you predict if something will form a solid solution? Well, there are some rules. It's actually called the Hume-Rothery rules, named after the scientist, one scientist, Hume-Rothery himself. And it outlines some basic principles on predicting if two components will form a solid solution. So inevitably, you're going to have some component that is in the minority phase, so you just have less of it, weight percent-wise, atomic percent-wise. And you have a majority phase, right? Typically, that's the parent matrix, the parent phase that you're trying to mix the second thing into, little by little, okay? So you'll have a solvent and a solute, very similarly to if you're thinking about the liquid state, where you're adding a solute into the solvent. You can have the same thing, but just in solid solution form. So some of the basic principles are outlined here in your lecture slides and also in your textbook. So if something has the same crystal structure, so if your parent phase has FCC, and you're adding a second component that typically also takes on crystal structure that's also FCC, then they're most likely going to mix, if the other three rules apply. So if there's atomic radii, about 15% difference, right? These are somewhat heuristic, so they're empirically determined that this will most likely work. There are exceptions, of course. So that's going on to the crystallographic site itself. Now, you probably have heard of steel, where there's iron and carbon. Carbon is much smaller than iron in terms of atomic radius. So you can incorporate carbon into interstitials. So in between the crystallographic sites that we have talked about, right? So for FCC, there are atoms at the corner and atoms at the faces. But there are gaps in between those atoms that we talked about. Carbon can go right there. But for a Hume-Rothery rule, let's say you have nickel and you have then copper. They have similar atomic radii, so they'll most likely make a solid solution. So same crystal structure, they're both FCC, similar atomic radii. Do they have similar electronegativity? That will also determine if you're going to form a solid solution. And then if there's similar valence, right? So if you have magnesium oxide, magnesium's 2+, will calcium 2+ go in there? You look at the valence, so 2+, substituting for another 2+, great. That doesn't mean that if it's different valence, it won't fit. And in fact, typically, if you have a higher valence, so a higher oxidation state, let's say you have something that's a +3 versus a +1, that's the same element, the +3 is more likely to go into the same oxidation state that was it for a +2, because it's most likely smaller than that of the +2, and so you can fit it in, right? Think about a chair, right? If you're wanting to occupy some space, right, and you're trying to put, like, I don't know, some some radii that's much bigger than the space that you have, that's going to be more difficult, right? So these are the guiding principles that will work for most solid solutions. So of course, we're not going to throw you a curveball and say something that obviously does not satisfy these rules and expect you to know them, right? So keep that in mind. There are always exceptions to the rules, but we'll talk about the cases that do work to begin with. Okay, so this was the example, nickel and copper. If you think about copper and gold, they do form, but in different stoichiometries than, say, 1:1. And we'll go into an example in the next slide regarding that. So the electronegativity between copper and gold, say, 1.4 and 2.4, similar, but obviously less similar than that of nickel. So nickel is going to more readily go into a matrix of copper than, say, gold would. But that's not to say that gold-copper solid solution couldn't form, and it actually does. Okay, so here's an example. If you're given, let's say, the information that you need: atomic radii, crystal structure, electronegativity, valence. If you had to pick between, whether or not aluminum or silver was going to dissolve in zinc. So zinc here is the solvent. And aluminum and silver are going to be the solute. They're going into the solid form of zinc. Okay, well, you just go down the list, right? You look at differences in radii. Am I trying to fit something that's really big into a small space? Or vice versa? Is it going to be energetically favorable? The delta R's, if you look here at silver and aluminum, zinc here is 0.332, and so aluminum is 0.1431. It's a little bit closer in atomic radii to that of zinc than, say, silver. So slightly favors aluminum in this case. Electronegativity here, it's 1.6. So the electronegativity for aluminum is also closer to that of zinc than silver to zinc. All right, so it's trending towards aluminum so far. Crystal structures, it does say HCP here, and these are FCC. Now, this brings up the point that we have not gone into great detail about HCP in general, other than to introduce it as a crystal system, and that it exists within, one of the 14 Bravais lattices. But where FCC and HCP can interact is the FCC 111 plane is hexagonally close packed. If you're just looking at the 2D projection of FCC 111 and HCP, the basal plane, so the bottom or top plane of HCP, they look identical. So you would need to have more information on that. So there is a plane where this could exist. And so if you look back at your chapter 3 crystallographic systems or crystal structure slide deck, you'll see this illustration in the slide deck and it's also in your textbook if you'd like to refer to that. And then when it comes to valences, so for aluminum, you can put aluminum 3+, so Al2O3 is a common compound where aluminum is in the 3+ state, oxygen is in the 2- state. So the fact that the valence here is higher than that of silver, it makes the aluminum atomic radii a little bit smaller, and thus it goes back to the first rule. And so everything is trending towards the fact that aluminum is more likely going to form a solid solution than that of silver, right? So I say trending because, once again, this is somewhat empirical, right? It's gathered data over time, and a lot of chemical hypotheses and theorems are also based on this. Like, this is a formalism that works, and so we're going to use it as a basis, even though we know there are exceptions, okay? Hence the terminology of trending. Okay. So here's another illustration of copper-nickel substitutional solid, a solid solution where the copper or nickel atoms are going into copper. Now, I've also talked about gold and copper, and depending on the temperature, it can form what's called a disordered system where you can have an average position. So could copper, sit here, or could gold sit at equivalent site? We don't know. It mixes around, so it doesn't matter. From one unit cell to the next, it could, it could change a little bit. So the average position is that you have a quarter of your sites be gold, and then 3 out of 4 be copper. Okay, that's what's called a disordered system, where there's an average site and there's no preference as to which site it's going to occupy. Below a certain temperature, for this particular system, you have what's called an ordered phase. So that means there's actually preferred crystallographic sites. So below 390 C, copper prefers to be at the faces, and gold prefers to be here. In this particular system, where gold is at the corner. Now, if you shift it all, right, it's still equivalent, but all that means is if one is at the faces, then it's always at the faces. And if one is at the corner, it's always at the corners, and they're interchangeable. But there's a preferred site. And so that's what we mean by an ordered system. Yes?
Are we going to need to know when that happens for each
Yeah. So all of these specific materials properties, the question is, are we expected to know when when an ordered structure will happen for a particular system, in this case gold copper? Absolutely not. I mean, I would, for any particular alloy of certain compositions, right, there's so many that any material scientist not working on a particular system would not really know. I mean, we have databases for that, where someone has worked out the entire phase diagram, which we'll go into in the next module. So no, absolutely not is the final and explicit answer. Now, if you were told this is a disordered system, then you know it's an average. Or if you're told you're operating in an ordered way, or you have an ordered phase, and it takes on FCC, then you would know, and you could work it out. But absolutely not. There's no reason why I would expect anybody to know any transition temperatures. I'm sorry? There are more. Oh, in terms of the number of atoms once you add up the fractions? So if you add up the fractions, right? So if copper is at the faces, how many atoms, what's the equivalent volume of an atom at a face? Oh, okay, so you got it, okay. Right, so you're not just counting atoms, you're counting fractional. So you do the math again. Okay, I'm glad I cleared that up in case you all were confused by that. Okay, so let's go to interstitials. This is a beloved system by every material scientist because this is what dictated the Industrial Revolution, and for many years, right? This system, I think if you went through a material science class for many years, you would just be given a phase diagram of iron carbon, and for 50 minutes you would just draw every single phase from memory at every single composition, and that would be it. Because this material dictated industry, right? A lot of materials are built with steel. There are entire classes dedicated to steel. We're only going to have 4 lectures on it, okay? But why is it important? It's important because you can put a carbon atom into the interstitial, and this absolutely dictates mechanical properties, corrosion, resistance properties, chemical stability, all of that, right? And so over the years, we've learned if we add in also chromium, stainless steel, we can have higher corrosion resistance than we have, which is regular steel, right? We give up maybe a little bit of strength in some areas, but corrosion resistance is more important sometimes, right? So anyway, the interstitials, even though it's a tiny atom, it absolutely changes the landscape in terms of mechanical properties. Okay, we talked a lot about metals. Let's talk about ceramics. Can we put a cation to substitute another cation? Yes. Similarly, can we substitute an anion with another anion? Also yes. So here's an example of magnesium oxide with some nickel 2+ in place of where magnesium was. Fine. You've achieved what's called electroneutrality. That means you have not changed the charge balance, okay? And so this is important because everything adds up to 0, all is dandy. When things are not, it looks something like this. So if you have sodium chloride, your cation is 1+, your anion is 1-. In the PDF that was uploaded, it was missing an extra half plane, so please add the extra atoms in there. So if you count all the charges, sodium is in blue, chloride is in green, so you have, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9, that's positive. So presumably for electron neutrality or charge neutrality, you should have -9, right? From the chlorides. Oh, sorry, I counted the chlorides when I meant to count the sodium. So, but it should not matter, so let's do it again. Sodium should be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then chlorides is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Charge neutrality. This is just a projection of one of the planes of sodium chloride. Now, let's say you want to put in a calcium 2+ or aliovalent. That just means it's a different charge. If it's an aliovalent substitution, you now have to remove one sodium atom out of the system in addition to putting in a calcium 2+ to maintain electroneutrality. Okay? So here you see, I'm just going to draw in a dashed line of where a sodium atom was. And then, so now if you count again, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? You're still ending up with +9. And then the chlorides are obviously -9 because I haven't done anything with the chlorides. So you have to maintain electroneutrality. So if you're putting in something 2+, you have to remove one of the 1+ to achieve. So now you have a vacancy and you have a substitution. Okay? So just do the counting. Similarly for anion, if you put in an O2-, you now have to take away what was once a chloride. I'll draw that in a dash circle here. And if you do the counting, you get to electroneutrality. Okay? Now, if you were just substituting sodium plus for potassium plus or lithium plus, doesn't matter, right? +1 goes in for +1, just like the magnesium oxide example. Magnesium is 2+, you substitute nickel 2+, doesn't matter. It's the same, so you don't have to do this counting of vacancies and such. It's only when the charges are different that you have to think about introducing vacancy. Actually, you don't have to think about it. The system will think about it because the material system will be chemically very unhappy and it will trend to this energetically anyway. But formally, this is how we represent it on pen and paper, okay? Okay, there are specific names for when we get these pairs. So let's say you take away a cation vacancy and there's also an anion vacancy, or you observe a cation vacancy and an anion vacancy. We have a specific name for that. We call that a Schottky defect instead of just a defect, right? They come in pairs. Or if the cation, let's say it was blue here, I'm going to draw a dash circle. Let's say it moved to one of these sites. Right? If it moved to an interstitial site, we call that a Frankel defect. So you see a vacancy and then you see an interstitial because it moved somewhere else in the structure. That's a Frankel defect. Okay? So if you just have a vacancy, then you just have a vacancy. But if you have these specific pairs, this is where you have these particular name systems. Okay? Okay, so now let's get to quantity. Okay, we talked about components, we talked about compositions. The phases we'll get to in chapter 10, but you could see here in this micrograph that things tend to start to have different phases here. Less important for until we get to chapter 10. When we want to talk about weight versus atomic percent, we're talking about, okay, for weight percent, we're talking about the mass of some element in the whole system. Right? I have 5% beryllium, weight percent beryllium. So I assume then that means I have in 100 grams that I have 5 grams of beryllium in there. That's weight percent, right? Atomic percent is different. I've talked about composition, and you can go back and forth with this relationship. And this is worked out and derived in your last lecture slide for this slide deck. It's also worked out in one of the examples in your textbook. There are 2 different approaches to it. Both derivations get you to the same answer, which are these 2 relationships, okay? Okay, so if we know the mass of one component, so we're talking about a 2-component system. If you have 3 components, then you just add on, the number of components you have, and you just manipulate the equation for the number of systems, number of components that are in your system. And so we can manipulate that with this example. I worked out this example ahead so that we can get to a more complex example later on, because I think with this example it's simple enough that you can go, work on it in your own time without much in-class explanation. But basically, if you have a system, let's say you're trying to weigh out 5 weight% of beryllium and 95 weight% of copper, okay? So how do you convert between weight% and atomic percent? Well, you can use a relationship where you can put in the weight%, and here we've deemed that beryllium is component 1. So this is your C1, which is 5 weight% of the beryllium. So just be consistent. Whatever you call 1, be consistent. Whatever you call 2, be consistent. You can switch it around if you want. If you want beryllium to be 2, fine, but just be consistent. So then if we say C1 is 5 weight% beryllium, we also are given its molar mass here. That's A2 is the molar mass of copper. So we're given that, 63.55 grams per mole. And so when you put in the numbers and you calculate it, you get something on the order of, let's say, 27 atomic percent. So you can see that the beryllium weight% is only 5, but the atomic percent is significantly higher than that. Right? This is just to demonstrate that obviously the 2 numbers are not the same, right? Because that's dependent on the molar mass of the system. It depends on whether or not, how many grams you have in a mole, right? Beryllium, you have 9 grams per mole. So even if you have 5 grams of beryllium, but you have 1 mole, that changes your atomic percent, because it has a higher percent of, in terms of the number of atoms in the system. And that all relates back to its intrinsic property, which is its molar mass, okay? So play around with this. It's a pretty standard, algebraic manipulation, so I won't go into too much detail to belabor the point so that we can move on to a more complex problem, okay? Okay, any questions so far on this particular example? Okay, quantitatively, I'll reserve the last little bit, I think. Well, actually, do I want to do that? Let me switch over and do the problem before we go on from point defects to line defects. Okay. I've posted something similar on the tutorial video, but let's say, because my handwriting gets very big very fast, I've decided that we're going to scroll, and I will not be confined to a PowerPoint slide. So we're going to do it through here instead. All right, so let's say you have, can everybody see that okay back there? Okay. So let's see, in this particular example, you have an alloy that's platinum. As I mentioned, it's used in catalytic converters. It's a very expensive element. So what people typically do is they'll add in some base metal that is cheaper, but you'll pay a price in terms of performance. But how much performance can you give up versus, paying a huge premium for using platinum, right? So people add in nickel. Sometimes they'll add in copper. They've added in other base elements to do these testing for catalysis. So now that you've incorporated nickel, you've incorporated 20 weight%. So clearly your unit cell, the lattice parameter for nickel is obviously different than the lattice parameter of platinum, right? And so you're given that here. You're given the different densities of nickel and nickel and platinum, and you're also given the molar masses of nickel and platinum. Obviously, you can look up these numbers as well, but they're provided here for convenience. They both have FCC crystal structure. And so the question is, what is the unit cell length edge for unit cell edge length for an alloy where there's 20 weight% of nickel? That means presumably for a two-component system, platinum is the balance of that, which is 80 weight%. Okay? And so let's do that. So the first step, we have to determine, okay, well, if the question is asking for unit cell edge length, and we're given density and molar mass, where have we seen this before? We've seen it when we were discussing perfect crystal systems, and we were relating the density to that of the number of atoms in that unit cell times the molar mass divided by the volume of that unit cell times Avogadro's number, right? We've done this calculation for copper only, and we've calculated the theoretical density of copper. So we know how to relate the unit cell edge length, A, to that of the given parameters of molar mass as well as the volume. Okay? So that's why I've already put this equation on there, is because we've seen it before and we've dealt with it. But what is different in this particular case is that now we're dealing with average, right? So it's going to be the average, the weighted average. The molar mass is now going to change because you have 20 weight% nickel and 80 weight% platinum. You don't have just nickel or just platinum anymore, so you can't just look up these average numbers. So that's what we have to determine. And then we also have to determine, well, we're solving for A, right? So we can rewrite this as the V cell, the volume of the unit cell, is just the number of atoms in that unit cell times still the average molar mass that we have to solve for, divided by the density, but the density is just going to be the average density of this 20 weight% alloy, 20 weight% nickel platinum alloy, times Avogadro's number. So it's clear that we don't know two things, right? We're solving for V cell because it contains our lattice parameter in there. That's the unit cell edge length. And we don't know A average and rho average. And that's what we're going to solve for. Okay? So that would be step 2. Okay, so let me rearrange. So we know, clean this up a little bit. We know that if we're given the weight percents, we can calculate what the average molar mass is going to be. So this is just the molar mass average. We know that we can take the weight percent of nickel divided by the molar mass of nickel plus the weight percent of platinum divided by the molar mass of platinum, which we're given, okay? And this is also equation, I didn't actually note the equation, but it is in your book, and it's right after equation 5.13, okay? So we can plug that in where CNI is 20 weight percent, and C platinum is 80. And ANI is already given. I'm going to scroll up, so everybody stay with me. I'll scroll back, don't worry. ANI is just this, and this is a PT, okay? All right. Okay, so if we do that, we get okay? I just plugged in the numbers that we just talked about. For the sake of time, I'm not going to be cranking out these numbers. You can do that as an exercise to follow this, okay? All right, let me go into text mode because it's very clear I need more space. Okay, so let's go back. So now we have to calculate what is the average density of an alloy that has 20 weight percent nickel and 80 weight percent platinum. So that's the density, and we know that the average density is given as so CNI is once again 20 weight percent, so CNI is 20. CPT is 80. You're given the densities of nickel and platinum. So here, I'm going to scroll. So this is just the row of nickel, and this is just the row of platinum. Okay. So if you plug that in, you get, I mean, I can, get something. This is 21.45. Okay. So this will give you something like 16.74 grams per mil or cubic centimeters, same diff. Okay. Okay, let's look at this number. Okay, let's look at 16.74. Does it physically make sense to you? Well, you have about mostly platinum, and platinum, the density is 21.45 if it were just on its own single component. If you have mostly that, it should be somewhat closer to that number, right? Just intuitively speaking. 16.74 is a little closer to 21.45. So already just having that sort of sense of like a physical sanity check, does this make sense before I go on? That's one way you can do it, okay? So now we figured, all right, we have this value that we didn't know before, and we have the weighted average that we didn't know before. So let's go back and revisit our equation that we were trying to solve for. So V cell, so it's in step 3 here, but I'm going to go back up to step 1 because it's already written here, and so to contain the work. So we know in FCC there are 4 atoms per unit cell. We counted this through together, right? So there are 4 atoms per unit cell in FCC. Our average is 133.18 grams per mole, molar mass. Our density is 16.74 grams per centimeters cubed times Avogadro's number. Okay, so this is actually, we put in all the units, it would look something like that. Okay, but that just tells us that this is all equal to a cube, right? The volume of a unit cell for a cubic system is just a cube, and we want to know what A is because A is the unit cell edge length. So we have to cube root the entire answer to get what A is, right? So if we cube root this, we get A is okay. Remember, you also need to convert from centimeters to what's more commonly reported for lattice parameters, which is nanometers and angstroms, okay? So I'm going to leave that exercise to you to do that unit conversion. But that should be it, okay? Any questions so far? You could also do a sanity check. You say, okay, well, nickel is tabulated. it's 3.52 angstrom. So this is just 3.75 angstrom. So this entire answer. Okay, so if it's 3.75 angstrom and platinum is 3.92, it's somewhere in between the two. So that's good. That's a physical check of whether or not your answer even makes sense. Because if your alloy is some mixture of two components, it should average out to something in between the two end members, right? So if you got something like 4 or 2 angstrom, you know you're in trouble because it's nowhere near or in between your two end members, okay? So nickel is smaller, platinum is bigger, so mixing them together, you get some average that's in the middle. Okay, somewhere in between, not exactly the middle, but somewhere in between, okay? So good sanity check, does this number even make sense, okay? Any questions about this example so far? It may or may not help you with your homework. Okay, no answers. We're going to switch back to talking about steps of dislocations. Okay, we talked a lot about point defects. You can have vacancies. You can have self-interstitials. You can have Schottky defects, Frankel defects. What happens when it starts propagating in a line? Well, we call that a dislocation. And if it's on the edge, as you see here that, at this edge, it's a little bit difficult to see, but it's coming out of the board. So what's happening is in this particular system, you have, atoms going this way, and then all of a sudden you have an extra half plane here, but that doesn't propagate to here, okay? So there's just an injection of a whole plane of atoms, and that's your dislocation. That's your defect. Well, the way we describe that defect in this particular instance is an edge dislocation or an edge dislocation line, right? And we draw that as this symbol. So whenever you see this perpendicular sign, you know somebody's trying to indicate that there's a dislocation, okay? And it represents that extra half plane. And so this part of it, as you can see here, is coming in and out of the page or in and out of the board, and your dislocation is here. Hence the perpendicular line. That's where your half plane ends, okay? It doesn't propagate beyond that line. Okay, what do we do with this information? Well, you see this quite a bit, and how do we describe it to another person? You see this quite a bit in metal systems, actually. And the way we describe the dislocation is with what's called a Berger's vector, and it's equal to 2r, r being your atomic radius. Because what you're saying is it's off by that half plane, and that half plane is occupied by these atoms. And so here you see that half plane here. And if I could, so that's where it would be if you could actually see through all the planes. And so what you're trying to say is, if I go around my normal lattice, I don't end up where I should end up because I have this dislocation. So the easiest way to do that is to pick a point, just start and say, okay, if my system were perfect, right? If it were perfect, let's say if I start here where it is perfect, there's no extra half plane just yet. If I go 3 in this direction, and then 3 in this direction, and then 3 in this direction, and 3 in this. If I go equivalently to the right as I do to the left, and down versus up, I get to where I was, right? So it's just completing the circuit. Like, am I crystallographically equivalent? The answer is yes, because you can traverse in equal amounts of unit cells, and you get back to where you were. Now, that's not the case when you have an edge dislocation. So it adds in an extra one, an extra half plane. And so if you start here now, and you go 2 in this direction, and 4 in this direction, then 4 in this direction again, then 4 in this direction again, and then 2, which is total 4, you see that you end up here in this red dot, okay? So there's a gap right here. And that's your Burger's vector. This. That is your Burger's vector. That's how we indicate there's a half plane there. There's a plane there that's missing, or that's missing beyond here. Okay. So this line that you see is actually a whole plane coming in and out. So it's not one atom that you're missing. Now it's a whole plane of atoms that you're missing. That's what the Burger's vector is telling you. Okay. So that's one example. If you just have a simple line dislocation, just one plane coming in and out. Obviously, they're going to have one moment. For the interest of time, I'll skip that example. But it basically just calculates your 2R for a specific system, that system being aluminum. But let's say you have now a screw dislocation. So what can happen is you have an extra half plane, but it goes like this, sort of like, one of those parking structures or whatever slinky that you can think about, right? It starts on one plane and it ends on another plane. Your dislocation just keeps on going. That's another type of dislocation. We won't go into it too much, mainly because there's enough to do with edge dislocation and also point defects, but I just wanted to point it out to you because if you're working in metallurgy, your microstructure and your mechanical properties will be affected when you have these screw dislocations. And you'll see that when you do microscopy and imaging. Okay, so these are just different renderings of edge and screw dislocation. Let me get to area defects. What you typically see and the materials you'll typically work with have these grains, right? So you could see here that in this particular material, these are grains, and they are touching each other. They're right next to each other like this. And so what you have is actually these grain boundaries where there's a lot of atomic mismatch, right? So it's not just one atom that's missing or a whole, a line that's now off from the crystallographic structure. It's a whole area that's off. And that's actually the real world. That's the material that you deal with every day. And so you see here within one grain, you can have, the area that I'm outlining here, you can have this particular area where the atoms pack very nicely in some crystal structure that you would expect. And then with another grain, the orientation can change a little bit, but right at the interface here, see, right at this interface, you can see that there are gaps and also misalignment. And that's okay, because in real world systems, right, you have these grains and you have polycrystalline materials because that's just how materials are made. And so unless you're carrying out some single crystal synthesis like Intel, where they grow extremely large ingots because they'll source, silicon from a very particular beach that has low impurity sand, and then they, ship it over to Portland and do whatever it is that they do to it to grow these beautiful large ingots that they can slice into their silicon wafers. This is what you mostly have, right? You have these misalignment of atoms. And then you can calculate and quantify the grain size. And so given the time that we don't have, I'll pick up on ASTM grain size number next time, okay?